they carried out kitchen experiments. And what is it about this wave flow of thin layers of a viscous fluid? Well, that's something you know very well from your everyday experience. Just yesterday, you could see that in the streets. So if you look at, during a rainy day, if you look at an asphalt road, particularly one that is inclined, well, water will be flowing downwards. However, it doesn't do so in a uniform way. Rather, we see these ripples. And these ripples, they form, well, so this is a paradigm system, a slope, a uniform slope, and a thin layer of fluid. So the fluid flow profile is something like this. Now, there is an instability that perturbs this flow and makes it develop these ripples. And these ripples are, well, the way this instability develops has been termed the Kapitsa instability. And so what happens is that large humps are formed, and these are the ripples that you see here, and in between them there's tiny capillary waves. And you can see them not only in during a rainy day, you can see them in discharge streams from dams and other hydrotechnical objects. Kapitsa derived a criterion for this instability to take place. So this is just one example of a kitchen flow that can be inspiring from a fundamental fluid mechanics point of view. But let me offer a couple of different ones. So whatever your favorite kitchen fluid is, or whatever your favorite kitchen phenomenon is, there is something interesting for everyone here. And I'll try to highlight just a couple of problems that might be inspiring. And in order to answer the question of why does it make sense to study culinary fluid mechanics, well, the kitchen is about being creative, just like chefs are creative in developing new dishes, new flavors, and new ways of presenting food. Especially if you go to fancy restaurants, well, then people come up with different ways to serve the same thing in a novel way. It is very accessible because that's our everyday experience, and most kitchen experiments can be carried out at home, although not all of them. And it is equitable, as in the barrier to enter this realm of scientific research is really low. And to give you another example of a person who entered kitchen science or entered big science through the kitchen is Agnes Pockels. So she lived in Germany between 1862 and 1935. She had a large family. She had 3 brothers. All of them went on to study physics. She wanted to, but she wasn't led to university because at that time, women were barred in Germany from studying physics. So she stayed at home and she helped her parents. And in doing so, and particularly doing the dishes, she got interested in the dynamics of interfacial layers. So what happens if you add soap to water? And she started observing the phenomena related to surface tension. And at some point she wrote a letter. Well, she couldn't publish her works because she was a woman with no formal education. So at some point she wrote a letter to Lord Rayleigh. And well, this is an excerpt from this letter. "My lord, will you kindly excuse my venturing to trouble you? I thought I ought not to withhold from you these facts which I have observed, although I'm not a professional physicist, and again begging you to excuse my boldness." It's very humble. "I remain with sincere respect to yours faithfully, Agnes Pockels." Immediately upon the receipt of this letter, Rayleigh got her paper published in Nature. And her subsequent works, well, you just look at the list: Nature, 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 Science. So that's quite a distinct, I would say that today we would say that this is quite a distinguished career. But back then, this help from Lord Rayleigh actually opened the door for her to do what she loved, so to do physics. And in her early experiments helped establish, well, the modern discipline that we now know as surface science. In particular, she the modern Langmuir-Blodgett trough, which is a device used to measure interfacial tension, is based on her invention, on her prototype of a sliding trough. So that's how she got into big science through the kitchen. So how about we wander around the kitchen for a bit to see what's interesting in there. Well, suppose it's dinner time approaching. Maybe not yet, but after the seminar, dinner time will be approaching soon. And suppose you want to have a cocktail before dinner. Now, one way to make it fancy if you invite someone over is to make these layered cocktails. And of course, well, how to achieve this sort of a structure where you have cocktails of different or layers of different colors. Well, obviously you take fluids of different density and you're pouring them carefully, but you need to keep them in order, right? So the densest at the bottom and then the lightest at the top. But of course you have to be careful because they can mix. Now, if they mix, well, then maybe you have experience with cafe latte. If you have a coffee with a layer of milk and they are separated, if you swirl the glass gently, you will see that this interface between coffee and milk starts fluctuating and waves develop. Well, you can study these waves, and in particular, so if you consider this idealized situation where you have two fluids, and you rotate the container, there's waves forming at the interface between different fluids, and the frequency of these waves is given by it's called the Brunt-Väisälä frequency, and it's proportional to the gradient of densities of the liquids that make this interface. And so, because if it's a fluid-fluid interface, this gradient is typically smaller than, at an air-fluid interface, they are typically slower than surface oscillations. And this is something fun to observe. Well, actually, we can see that not only in the kitchen, but we can see that also on the scale of the whole planet. So what you see here is a satellite photo of the island of Trinidad in the Caribbean. And here, these ripples that you see are in fact wave trains that develop not on the surface of the ocean, but in between layers of different salinity. So water with different salt content doesn't necessarily mix very well. It takes time, and so you can have a stratified structure with different layers of different salinity, and at the interface between these layers, there are these waves that can develop. This has practical consequences also for sailing. So this gentleman here is Fridtjof Nansen, a famous Norwegian explorer of the beginning of the 20th century, and he noted in 1893. He noted in his travel diary that he was traveling by boat called From, and this From was caught in dead water, or what he called dead water. So he noted, when caught in dead water, From appeared to be held back, as if by some mysterious force, and she did not always answer the helm. In calm weather with a light cargo, From was capable of 6 to 7 knots, but when in dead water, she was unable to make 1.5 knots. And so this dead water was a mysterious force that pulled the ship back. But in fact, his country fellow, Vagn Ekman, was able to explain this phenomenon of dead water precisely by the fact that if you have a boat moving with a certain speed, the increased drag force on this boat might be related to internal waves that form at the interface between different layers, so layers of different salinity. And so that was by just bad luck that Nansen's boat was traveling at a speed that would somehow resonate with the eigenfrequencies of these waves and enhance them, and thereby increase the drag force. Okay, so let's go back to our cocktails. So if you want to make things fancy, you can make a cocktail with a denser layer on top of a less dense layer. Or, well, in this case, in the laboratory experiment, you can take salt water, which is denser, and fresh water, which is lighter, and make this inverted cocktail. Well, what would happen then? Obviously, the system is unstable, so it will eventually mix. But how does it do so? Well, it does so by means of Rayleigh-Taylor instability. So, yeah, this is a video of an experiment. So what you see is we're going to have two layers of fluid, so the denser fluid above, a metal plate, and the lighter fluid. We open the metal plate, and the lighter fluid travels upwards, and the denser fluid travels downwards. And they do so by developing these plumes, the plumes that travel upwards, and then there is a backflow of this denser substance downwards. And of course, eventually it's chaotic and the mixing region fills the entire fluid domain, but the growth of these plumes is something quite beautiful, and this is essentially the Rayleigh-Taylor instability. Now, what if these fluids in our cocktail could mix? Well, one thing is Rayleigh-Taylor instability if you make an inverted cocktail. But even if you don't, they will eventually mix if you swirl them. And another phenomenon that develops during the swirling motion is mixing by relative motion of layers of fluid, of different fluids. If they are moving past each other, so if one layer of fluid moves past another layer of fluid with a different speed, then any surface disturbance will be enhanced by the fact that this shearing motion of the top layer will drag this crest and push down this trough, and so a swirl will form. And this swirl will form either in your cup of tea, or it can form in nature. And so this is an example of a cloud, and this cloud is moving at a different speed than the surrounding air. And of course, the surrounding air is pulling the top layer of the cloud, thus forming these eddies associated with the Kelvin-Helmholtz instability. Now, well, you could say, what does it have to do with the kitchen? Well, here is one example. So Rayleigh-Taylor instability can be induced in the kitchen, for example, in this shot of vodka or any other strong liquor, by the fact that, well, the mixture evaporates. If you leave it for long enough, it will evaporate, but the alcohol evaporates faster than water. So what happens is that in this top layer, you will very soon have a layer of fluid where the alcohol content is lower than in the bottom. And if the alcohol content in the mixture is lower, then the density is higher. So you end up with a situation where you have a layer of denser fluid on top of a lighter fluid, and so you will develop a Rayleigh-Taylor instability. And if you employ this interferometry to visualize these plumes, you can end up with something like this. And so this is a visualization of these plumes where alcohol concentration is marked in color. Okay, well, another interesting phenomenon, since we mentioned alcohol, is that maybe some of you prefer wine. And if this is the case, then you're familiar with this phenomenon. If you swirl wine in your glass and you leave it be, then it might develop these structures that are called tears of wine, very poetically. Now, how do they form? Well, this problem has attracted the attention of great minds of the 19th century, and in particular, the first one to give an explanation of this phenomenon was James Thomson, so older brother of Lord Kelvin, and he was a professor at the University of Belfast, and he wrote a paper in 1855 in the Philosophical Magazine on certain curious motions observable at the surfaces of wine and other alcoholic liquors. So I presume there was a fair amount of observation that was put into this paper. Now, the explanation that he put forward was the following. So if we have the glass of wine, there is a meniscus here, and in this meniscus, the alcohol evaporates. Because alcohol evaporates faster than water, then the local composition of the solution, so this wine, changes. And that leads to not only a variation of density, but also a local variation of surface tension. And this local variation of surface tension results in the fact that there is a layer of fluid where alcohol has evaporated more and the surface tension is higher, and a region where the surface tension is lower and there's more alcohol in the mixture. But this will induce a flow called the Marangoni flow that is induced by gradients of surface tension. And so it will push more fluid upwards. And so this thin layer will grow upwards until it is destabilized by gravity. And so this destabilization by gravity is what produces these tears. In fact, this is an area of quite modern research, because the formation of this ridge that is fueled by the fact that there is a surface tension gradient along this slope, this can be described in the language of shock waves, and this is called a reverse undercompressive shock. And so, well, people have been observing the formation of this ridge and the dynamics of the formation of this ridge, and trying to explain this quite recently. So this is an area of active research. Now, it might be that wine is not to your liking. but you might be a bubbles kind of person. And so champagne might be your drink of choice. I mean, I wish. But so champagne is a fascinating fluid. Why? Because it has bubbles. Where do these bubbles come from? They come from secondary fermentation. So you ferment your wine and then you ferment it again in the bottle. And so the yeast in the bottle consume sugars and they exhale CO2 and they exhale alcohol. And so there is so much of these bubbles in the bottle, in a typical bottle of sparkling wine, that the pressure inside is about 5 atmospheres. So this explains why we need so thick bottles to transport these fluids. So what it is effectively, it's a supersaturated liquid. And so if you open a bottle of champagne, you'll have to deal with a vigorous release of this excess gas. And so this phenomenon is associated with foaming or effervescence. Now, what happens if you open a bottle of sparkling wine? Well, everyone hears that. There is a pop. And this pop, if you take a fast camera and if you record what's going on there, well, this is time in microseconds here. So this is 1 millisecond, so it's fairly fast. But what happens here, well, we open the bottle, so suddenly the pressure near the neck drops from 5 atmospheres to 1 atmosphere. And there appears this blue mist. So what is this blue mist? Well, in fact, it turns out this is freezing water vapor from the air. Because when you drop the pressure from 5 atmospheres to 1 atmosphere in a fraction of a second, a tiny fraction of a second, what happens is this mixture of CO2 and water rapidly decompresses. And so it adiabatically cools down by about 90 degrees Celsius. So what you see here, this tiny blue mist here, is freezing water and CO2. You can actually see more. You can see these fringes here. So there is areas, there is a clear division, a horizontal line, and so this is a supersonic shock wave that is associated with this rapid change of pressure. And so there's quite a richness of phenomena in a bottle of champagne. Okay, but then champagne is about bubbles. Bubbles are super important for sparkling wines. Bubbles are what makes sparkling wine really so tasty, and we'll explore why. But if you don't believe me, try to wait long enough until there's no bubbles, and this is not very drinkable. Now, if you look at bubbles, well, they form in various places all over the glass. It turns out that in a champagne there's a kinetic barrier for nucleation. So if you create a bubble in champagne, a random bubble of a random size, it will not always grow. To grow, it needs to be of a certain size. So this size is needed to overcome van der Waals forces. It turns out that the critical radius of a bubble to grow is given by the surface tension of champagne, which is about 50 millinewtons per meter, the atmospheric pressure and the saturation by CO2. So the difference between the saturation pressure of CO2, 5 atmospheres, and atmospheric pressure. So this is about 4. And so it turns out from this calculation that if your bubble is about 0.25 of a micron, so 250 nanometers, then it will grow. But then we need to have these bubbles of this critical size in order for these bubbles to grow. So how does it happen? Is that from a homogeneous fluid, you generate these bubbles. You can wait for fluctuations, but then you would have to wait a really long time for these large fluctuations to develop. Now, it turns out that there's 2 ways of inducing nucleation. First is so-called natural nucleation. So inside champagne, but also in the glass, there's tiny filaments of cellulose. There is dirt of various kinds, and this dirt can store pockets of air. And these pockets of air can be large enough for the bubbles to form. So in order to start nucleation, you need some sort of seed, and this seed can be provided by naturally occurring dirt, which is present both in the bottle and in the glass. But there's another way. There is artificial nucleation. For example, you might notice that if your glass is somehow rough or has some impurities, they might serve as sources of this nucleation. In particular, in this glass, this ring was shaped by laser beam. So you can shape your glass, and of course this is interesting for people who make champagne glasses. So you can shape your glass in such a way that it will nucleate from this shape, and you get this fancy trail of bubbles. Of course, these bubbles grow. In fact, they grow in such a way that the diameter increases linearly with time as they go up, and you can propose a relatively simple model that explains this. But let's move to something more practical. Well, it turns out that if you are a champagne fan, the way you pour your champagne really matters. So who prefers, let me do a little vote, who prefers to pour champagne like this, to have a glass that is straight? Okay, and who prefers to pour it to a tilted flute? Definitely more. But why? Well, it does bubble less, and these bubbles are important. And so it turns out, well, if you do infrared imaging on a glass of bubbles when you pour your champagne, it turns out that you lose much less CO2 when pouring into a tilted flute. And what I want to convince you about is that you should have as much CO2 in your glass as possible. So this is definitely, in this aspect, this is a better way of pouring. And so why do these bubbles matter so much? Well, first of all, if you do light sheet imaging on a glass of bubbles, you might find out, and if you do time lapses, you might find out that these bubbles, they entrain the fluid, and so they induce mixing in the glass. This mixing is important because that brings the aromas from throughout the glass to the surface. And when these bubbles reach the surface, well, they burst, and by bursting, they release all the aromas that we look for in a glass of wine. And so, yes, without bubbles, this is not the same kind of fun. Now, it might happen that your funding is lower than to afford champagne, so you can try doing experiments with beer. And then, again, beer is a fascinating fluid, because if you deconstruct a glass of beer, well, first of all, if you compare bubbles in champagne and bubbles in beer, those in champagne are clearly larger, and this is because there is less dissolved CO2 in beer. There is the supersaturation level is lower. But then you might be beer is richer in the sense that you have foam, so there's the fascinating area of the physics of foams and what stabilizes them. Then these, cellulose fibers that act as nucleation sites are all over the place. These bubbles get to the surface, they burst. And so there's many unanswered questions, fundamental questions even, in a glass of beer. Okay, so after this long session of pre-drinks before dinner, you might be ready. You might be ready to cook. And if you, well, at least one way you can do cooking is to use a frying pan. And my grandmother used to have this idea of how to assess whether a frying pan is hot enough. What do you do? Yeah, drop a bit of water. Okay, so let's do this experiment. So what if we drop it on a hot, oops. Yeah, so here I did this experiment myself. I pour a drop of water, it sizzles, so that means that the frying pan is hot. But what if you forget about this frying pan, leave it for longer, and it gets very, very hot? Well, then you might observe that your droplets might not sizzle at all. Instead, they might do these funny, well, they might just roam all over the place, but they might stay stable. And well, this guy behaves like there is no problem with this hot surface. It doesn't evaporate so much. Its lifetime is relatively large. Yes, well, I'll get to this. But so what's going on? Because we learned that the flux of heat is proportional to the gradient of or to the difference of temperatures. So there's clearly something wrong with this picture if you go from hot to very hot, and the lifetime of these droplets increases. So this was puzzling already in the 18th century, and the first person to describe it in full was a German physiologist or a doctor, Johann Leidenfrost, 1756. Well, what happens is that if you just sprinkle a droplet on a hot plate, it will start boiling. It will start boiling everywhere and throughout its volume, so pockets of vapor will form, and and of course this will happen the more vigorously, the larger is the temperature, the higher is the temperature of the pan. However, then you reach a state which Leidenfrost described, where the rate of heat transfer, which is depicted here as a function of temperature, has a drop. Well, this drop is associated with the following fact, that if the pan is really, really hot, then immediately upon impact, there is a tiny layer of vapor of a thickness of about 100 microns created underneath the droplet. What this layer of vapor does, it works like a cushion that insulates the droplet from the pan. And the thermal conductivity of water vapor isn't very high. And so this insulation can work to increase the lifetime of these droplets considerably. And in fact, the same thing happens when you pour liquid helium or even liquid nitrogen. So the reason why you can put your hand in liquid nitrogen and pull it out and be okay is precisely because the difference of temperatures between your body and the liquid nitrogen, minus 195 degrees, I think, Celsius, is so large that immediately upon impact, a thin layer of nitrogen is formed that insulates your hand. Of course, if you do it for too long, then you will not take it back. Okay, so now that we are in this world of thermal phenomena, let's try, and our pan is already hot, let's try to heat the water up. So if you start heating a layer of water, so the temperature of the pan is higher than the outside temperature. That's the whole idea of cooking. And you have a layer of fluid of a certain thickness. Well, what might happen, you can fall into two scenarios. You can either have conduction of heat from the bottom layer, from the bottom plate to the top free interface, or you can have convective transport, which is more irregular. Now, what decides between the two, the criterion that decides, well, it's known as the classical hydrodynamic instability of the Rayleigh-Bénard convection, and the criterion is the Rayleigh number, which quantifies the relative importance of diffusion of heat to advection in a flow, and it's given by this combination of parameters. So the density of the fluid, the gravitational acceleration, the thermal conductivity of the fluid, the thickness of the layer of fluid, the temperature difference between the bottom and the top layer, the viscosity, and finally thermal diffusivity. And so in the simplest setting, if the Rayleigh number for your particular fluid and the particular layer of fluid exceeds about 2000, you might see the onset of convection. And in fact, this is what we very often see in a pot of water that's heating up. You have surely seen these patterns in a pot in your kitchen. And so these patterns signify the fact that this transport occurs via convective cells. So there are regions where the fluid is flowing upwards. So the hotter fluid is flowing upwards, and the cooler fluid is sinking downwards. The same you see in a cup of coffee. If you drink your coffee with milk, you add cold milk to hot coffee, and then you will see this convective patterns where hotter coffee raises up and the colder milk plunges down. Okay, so we are cooking now. So some of you might be into making pancakes. And so I want to convince you that making a pancake is also an exercise in a relatively low Reynolds number flows. And so what happens when you pour pancake batter onto a pan? Well, you have a fluid of relatively large viscosity, and therefore the Reynolds number associated to this flow, which tells you how much viscosity matters over inertia, is relatively low. And so we encounter something called the viscous gravity flow. And from the low Reynolds number hydrodynamics, you can in fact derive a formula for how a radius of such a drop or puddle of pancake batter will spread in time, and it spreads like a square root of time. In fact, it's more complicated because a pan is typically hot, so this would be true for a fluid that's of constant viscosity, but in pancake batter on a hot pan, we have a phase transition, which complicates things. But this works very well for a drop of honey, for example. Now you can say more, because people have also studied, and this is a fairly recent paper from Physical Review Fluids 2018, what's the optimal way of spreading pancake batter on a frying pan? Do you know the answer? Yeah, tilt it, but not only tilt, but also do this little twist. And it turns out that if you try to optimize this, well, this is what it looks like. And so this is fairly close. I mean, our everyday experience is often about optimizing things. Okay, well then we can apply the rules of physics also, well, not only to frying pancakes, but to frying something more hardcore. For example, if you like your steaks, well then depending on what kind of a person you are, then you like your steak in different ways, either well done or rare or medium rare. Well, pick your favorite. Now it turns out that you can, well, this has been studied. The soft condensed matter has a perspective on moisture transport in cooking meat, because cooking meat is about transporting moisture. So in order to cook up, and pun intended, to cook up a model that would grasp very well what happens to your steak during frying, well, then you have a system of coupled equations, because you have moisture transport due to gradients in swelling pressure, which is a pressure that occurs internally inside the steak when you raise the temperature. Then this liquid moisture evaporates, of course. There's a coupled heat conduction inside the meat, coupled to this increase of swelling pressure. There is convective heat transport by this moisture flowing throughout the steak. And of course, there is dripping of this liquid moisture from the surface, and heat transfer between meat and airflow. But if you get these all together, you can get a really decent estimates of the temperature and moisture profile during cooking of beef. And so this is where mechanics of continuous media is actually able to predict very well what happens inside this cooked meat. But of course, eating too much red meat is not healthy, so I encourage you to eat your greens as well. However, if you're more mathematically inclined, you might stay in the realm of meat, and you might want to explore the mathematics of burger flipping, for example. That's also a recent paper from 2022. So the problem is the following: you have a hamburger here. So if you're putting it on a pan, then you have a hot plate, and you have air, which is cool. And then what happens? Well, heat diffuses in. But then the question becomes, when do you flip your burger? If you flip your burger, well, you reverse this scenario, but then you have to time it in such a way that you optimize your the way it's cooked throughout. So is one flip enough? Or two flips enough? When to make the first flip? Well, I won't give you the answer here, but the answer is there in the paper by Jean-Luc Tifot. But I think two flips are optimal, but then you have to time. The first flip needs to be faster than the second. And the interval between the first flip and the second flip is larger than between 0 and the first flip. Details in there. Okay, and then there are various kitchen substances that you are used to working with, and they act as models of fluids that are called non-Newtonian. So we are used to water being a Newtonian fluid, so a fluid that its properties are fully defined by its viscosity. Now, most kitchen fluids are not Newtonian, so their viscosity in particular depends on what happens with them. So many of you, I'm sure, have the experience with shear thickening fluids, such as a mixture of cornstarch and water. It's a fluid that behaves in a almost like a solid when you grab it very fast, but when you leave it, then it flows. So it's an example of a fluid that thickens, so its viscosity increases when you increase the forces acting on this fluid. Now, there are fluids which are called thixotropic, where the viscosity depends on the shear rate, on how fast you're shearing it. And in particular, jam is a substance like this. So you want your jam, or the food producers want their jams to spread easily, but once you spread it, you want it to stay. You don't want it to drip, to keep dripping. So there is some engineering that can be done to to make a substance that spreads easily but then stays. And so these fluids are thixotropic, so they remember the history of what happened to them. Now, whipped cream is an example of a Bingham plastic. So this is a fluid that you need to exert some critical stress on it for it to start moving. Mayonnaise is like that too. Then there is fluids that contain polymers, and then they have quite a complicated stress response. For example, egg white has this Weissenberg effect, and Weissenberg effect is about if you put a rotating rod into a polymeric fluid like egg white, and you start rotating it like a mixer, a kitchen mixer, then it might climb up. Which is not what it doesn't happen with Newtonian fluid, but it happens if a fluid has polymers that stretch out during this motion. And finally, a way to teach students of this all are examples of rheology. So rheology is the stress response of different fluids. One way of understanding this rheology is through kitchen experiments. And during the pandemic, a group from the University of Chicago proposed this, oreometer. So typically a machine that is used to probe the stress response is called a rheometer. This is an oreometer, and you have an Oreo cake here. And depending on the temperature of this cake cream, well, this behaves differently. So you attach basically a driller to an Oreo cake, and then you induce a velocity profile, and you might measure its stress response. So instead of rheology, you can do oreology with oreometers. Which is, and this is in fact a setup that was realized at the University of Chicago, or at students' homes for that matter, during the pandemic. Okay, so maybe we've had enough of food, and maybe it's time to drink something, well, stronger, in the sense that I like a coffee after a meal. Now, you might be an espresso person. Who likes espresso coffee? Some. In some circumstances. Well, brewing espresso is a religion. So some people are so much into it that they believe in certain ways and how espresso should be made, what is the perfect espresso. Of course, that depends on where you are, because in Italy, the perfect espresso is an Italian espresso. In Norway, it's something completely different. But typically, if you brew it for 20 to 30 seconds, you get something that is called the perfect espresso. It's sweet enough, it's not bitter or ashy. That happens if you wait too long, if you brew it for over 30 seconds. So then we have an over-extracted espresso, or we can have an under-extracted espresso when you brew it for too short, and then it becomes sour and it has these vegetal notes. So what is the brewing of espresso from a physics perspective? Well, in fact, coffee is a fascinating fluid. So first of all, it's a mixture of grains of different sizes. So it's a porous medium. We expose it to flow, and this porous medium then dissolves. And so what we have is a porous medium with a structure that is evolving. In this structure, there's often channels forming, and these channels can focus the flow. In fact, what we did, I'm doing some coffee research in my lab. Well, I'm a theorist, but I do have a laboratory, and it happens so that we have a coffee machine in there. And we do some measurements on this coffee machine. So what you see here is an espresso, is a coffee cake. So what's left after brewing an espresso, it's a coffee cake, but put in an X-ray computer tomography machine. And what we see here is a channel that has been formed. I'll show you this channel in a second more. I'll show you it now. So this is a 3D image of this coffee cake with a channel that has formed. And this channel is not a good thing for coffee because it focuses the flow. And so the flow goes through at the rate you would expect. So you get your 30-second espresso, but it doesn't dissolve the coffee as much as you would like. So you get something that is an under-extracted coffee. And of course, well, to understand flows in porous media, people typically employ Darcy's law. Mr. Henri Darcy is known for this relationship between the flow rate and the applied pressure difference. So the more the pressure difference you apply, the more flow you get. The flow rate is inversely proportional to the liquid viscosity, and this coefficient of proportionality K, which describes the response of the medium, is called the permeability. Now, he did his research, or he coined this Darcy's law while working for the city of Dijon in France, and working on on supplying water to the fountain system, to the public fountain system of the city. And so he studied, on this occasion, he studied the flow of water through a pipe filled with sand or with other porous material. And so Darcy's law describes this linear response in terms of flow to an applied pressure gradient. Now, coffee is a complicated porous medium because it's typically polydispersed. Now, depending on your favorite method of brewing, either French press or Chemex or drip coffee or espresso, well, then you have to grind your coffee finer and finer. Typically, and this is what we also see in our lab, the particle size distribution in ground coffee is a bimodal distribution. So you have a lot of these large particles that are about 500 microns across that are called boulders. And there you have the second peak are called fines, and these are typically sub 100 micron particles. They also dissolve, so it turns out that that life is more complicated because once you prepare your coffee by tamping, by ensuring that the sample is homogeneous, that you have a fixed bed thickness and you have the same grind size every time. Well, and then you measure how much water you pump through and how much coffee you get, and this is what we did. These are our measurements from the lab. There is a certain delay between the pumped water mass and the coffee mass because of this water soaking this coffee soaking water in. But then this is not quite a linear relationship, and well, maybe next time I'll tell you, because we're just now writing a paper on breaking the law of Darcy and how coffee breaks the law of Darcy. It's not a linear porous medium, and its pressure response is quite complicated. Well, anyway, you might be, oh, and now it rotates. So you see that this channel that formed in our coffee, so the water went through here and then it spread all over. So this is the bottom sieve, and the coffee, your ready coffee drips down here. Now, even if you're not a coffee person, you might know this dark side of coffee, the coffee ring effect. So if you leave a drop of coffee or tea or wine on the surface, then what happens is that this drip dries out and it leaves this stain, and the stain is particular in the fact that the rim of this stain is darker than the interior. What's the explanation of this? Well, this stems from the fact that if you have a droplet that's uniformly evaporating, but its contact line is pinned, it thins out in a non-uniform way. And because its thickness changes differently in different places, there is a flow that's induced inside, and this flow brings particles that are suspended in this fluid close to the rim. And they stay in there, they get trapped in there, they don't come back, and then they form this coffee ring. Now, if you're not into coffee, you might be into tea. And then there is a problem that if you stir your tea, well, this is a magnetic stirrer, so we're stirring the tea, and we'll stop it in a moment, and we'll see what happens. So we stop it now, and you see that tea leaves, they gather, well, now it's evident, they gather in the center. But this is somehow counterintuitive, because in rotating systems, we would expect things to go outwards by these centrifugal forces that they feel. But then they go to the center. And this was a problem that Albert Einstein was posed by Schrödinger's wife. She asked him this question, he didn't know, but he worked on it, and he wrote a paper on it. It has a different context. He wrote a paper on the erosion of riverbeds, but it's the same mechanism. Well, it turns out that what happens in the what happens in there is that as we rotate the whole container, then to satisfy the no-slip boundary condition on the surface of this container, well, the fluid has to develop a secondary flow. And the secondary flow is something that circulates inside and drives the leaves to the center. Now, if you stop stirring the fluid, then it will naturally come to a stop by viscous dissipation. The typical time it takes is called the Ekman time. And so it's proportional to the thickness of the water layer squared, divided by the viscosity, and divided by the initial rotation rate. And for example, if you cook poached eggs, you might be interested in how long does it take. You swirl your water, and then you put in your egg, and then you wait for it to cook. So if you have a 5 centimeter thick layer of water at omega of 0.25 hertz, and the viscosity of water at 90 degrees, then it takes about 2 minutes. And this is maybe useful for cooking poached eggs, but it's also useful for sorting blood cells from plasma and for filtering beer, so more fundamental applications. And because, well, time flies fast, I will skip the digestive. But I'd like to convince you that it's in kitchen flows, it's only imagination that limits us. And there's plenty of very, very interesting problems that can be attacked that belong to different parts of physics. They have an underlying theme of fluid mechanics and flows, but there's more than meets the eye, and definitely it's only our curiosity and imagination that limits us. And before I finish, I'd just like to advertise that this and more stories are written in a paper that we started. So we wrote a little review paper on culinary fluid mechanics with 3 colleagues from, well, 2 from the US and 1 from Norway, on these culinary fluid mechanics, and we did it also in the pandemic when we were out of our labs, and we started exploring the literature in search of kitchen phenomena that bear a deeper fluid dynamical meaning. So if you're interested, please have a look. And we structured it like a menu. So we start with kitchen sink fundamentals, so the fundamental laws of physics that apply to kitchen fluid mechanics in particular. Then a little bit of pre-drinks before dinner, so multi-phase flows as drinks and cocktails. Then we talk about complex fluids. So this is a soup starter that you might be interested in. Moving on to the main course, which is thermal effects, and finishing with a dessert, which is an occasion to talk about viscous flows, and then concluding with coffee and tea, which are excuses to talk about granular matter and porous media, or nonlinear flows and turbulence. And finally, someone has to do the dishes, but this has to do with interfacial flows, which can be quite fascinating. And so with this, I'd like to thank you for your attention, and I'm happy to take any questions.
Thank you, Maciej, for amazing talk. Right, we have time for questions, comments to the speaker. Please, Bożena.
You were talking about convection, but in the case of water, when it's boiling, this convection looks quite stationary. But if you make a jam and you are quite close to the end, so this liquid is very dense, then the time scale is very eruptive, so nothing happens, and then you have something like a volcano shooting
you
up
have these
your
bursts
which
of
is
bubbles,
very hot. It's jumping to 30, 40 centimeters even.
Yes, yes. Well, a jam becomes a fluid of quite a complex rheological response, and if you add an extra phase to it, so these bubbles, yes, that can get quite difficult to analyze as well. But I haven't seen any systematic study of this, so this is perhaps a fascinating topic. We'll let you know if we start working on this.
Nikolai?
Okay, thank you very much for a fascinating talk. I would like to return to the problem of pancakes because I prepare them quite often and I even experimented with them. So the behavior very much depends on the amount of water you have in your dough and on the viscosity. But there's much more interesting things going on. If you turn the pancakes over, sometimes you see the formation of bubbles of steam inside the dough, which is also quite fascinating and which affects your result. And there's also the question of the pattern of darker parts of the of the pancake, which depends on your temperature and other things. I'll be happy to talk with you about that because it's
Absolutely. So
super topic.
the dark spots is the Maillard reaction. So the sugars turn brown when the temperature difference is sufficient. But of course, the formation of bubbles depends both on the composition and on the temperature of the plate. And well, I'm sure there is a fascinating balance to be made there of the time scales of transport of heat and moisture inside.
Wojtek?
Yeah, thank you very much. I have a feeling that it was a TED quality talk, so very well polished and prepared and very entertaining. I have 2 comments actually, and I'd like to hear your response. First would be, I'm a numerical cosmologist, a computational cosmologist. We use supercomputer simulations to study how the galaxy evolve in cosmic and large-scale structure. You will be surprised, maybe that's not actually not a surprise that the field of the galaxy formation on those scales is sometimes called, funny way, gastrophysics, because of the galaxy formation, because many phenomena are shown here, like mixing Kelvin-Helmholtz instability, Rayleigh-Way cascade. It also appears in the large-scale structure cosmic web because we have a hot and cold intergalactic medium. Of course, it's gas, not fluid, but gas is fluid, as you know perfectly. So I think you would be surprised. Maybe look up a little bit interesting if you want to add that there's even universe on all scales do some kind of a cooking, and it's important.
Thank you. I'd love that.
Yeah, and second of all, I think you should definitely try to convince our Ministry of Education to sell some of the stories to our children in schools, because this is a fascinating way to really teach physics. Moving away from train A, from station B, goes to its kinematics. This is actually, because there's a physics behind it and it's really tangible, I think would be great if you convinced any of you example and physics goes to the textbook. So
I agree. Let's make gastrophysics great again.
yeah, thank you.
Okay, any other questions or comments to Maciek? Right, I just want to say that I fully I agree with Wojtek's comment. Part of my motivation for inviting Maciek was to actually have inspiration for experiments for my son, for example. Yeah, so I have one maybe last question. So
maybe this was heavy on the drinks side, but there's fascinating
Okay.
flows in other directions too.
For later years. Right, so one technical question about this nonlinear response to pressure in coffee. Like, do you so you observe it empirically, but do you have some model that predicts it? Like, do you understand why?
Yes. So what we see briefly, what we see is that at low pressures, the coffee behaves like what happens initially, the coffee is getting dissolved, and so this is quite complex. But then if you wait long enough, way past the good espresso, if you wait a minute or 2, then the flow rate stabilizes. Because all that was to be dissolved already has been dissolved, and you have a stable flow rate. And now this flow rate, well, how it compares to or how it scales with pressure, initially for low pressures you have a Darcy-like medium, but for higher pressures you see that this flow rate starts becoming independent of the applied pressure, and we think this is because the coffee bed is compactified, so the pressure there is certain porosity, and this porosity decreases because the high pressure of water actually collapses the medium, and so the pressure, the external pressure, rebuilds the medium or affects it in such a way that it collapses, it compactifies, and because of that, this increases the resistance to flow in such a way that, roughly speaking, the flow rate becomes independent of the pressure gradient.
Okay.
So stay tuned because we're just writing up the paper.
Thanks. Maybe somebody online wants to ask a question. Okay, like if not, let's thank Maciek again for amazing talk.
Thank you.